Hello everyone, Dr. Zia Tahir here. This video tutorial is 2D bridge truss analysis in Abaqus CAE. So that is one vertical frame of bridge truss. So bridge trusses are very commonly used for short span and even sometimes for longer span. As you can see, these are the bridge trusses, and then that is its one of vertical frame, so which I'm going to model. So all members are made up of a material having modulus of elasticity 30 gigapascal and Poisson's ratio of 0.3. Horizontal members, these horizontal members, they have area of cross section as 0.045, and diagonal members they have 0.02. And required is deflection of each joint, like at each node, and then axial force. So this is problem 2.1 from chapter 2 bar elements. From book Introduction to Finite Element Analysis using MATLAB and Abaqus, and that is a chapter 2 bar element, and here is problem 2.1. so that is the problem 2.1. So the solution of this problem using MATLAB is available in the book, so I am going to verify my Abaqus result or check my Abaqus results by comparing them results given in the book. Steps for this analysis, there are main three steps: modeling, analysis and results, and these are like summary of this video tutorial. So like as you create part in the modeling, then material, create section, assign section, create mesh, create instance, create step, modify field output or create field output, create load, create boundary condition, create job, and then visualization using field output dialog, and then prob value for deflections or displacements, and then for axial forces or member forces need to export normal stresses to Excel and then calculation there. So before starting, you need to understand that Abaqus doesn't have any set of units. So you have to use your own set of unit, like as in System International, Newton meter, Pascal, or in Imperial, pound, inch, and PSI. So these are the two set of units which you can use, or otherwise you can use Newton millimeter and megapascal as well. This question, dimensions are in meters and area is also in meter, and modulus of elasticity is in Pascal, gigapascal. So and then loads are in kilonewton. So I am going to use one of unit, but this is you have to decide outside from Abaqus. So this is how Abaqus looks like. So here you have Abaqus CAE 2020. So in the view, I can graphic option, so I can change background of viewport, and I turned it to white. Okay, and then you need to first set work directory. So work directory is a folder where you want to save all your analysis, model and result. Save all model and results in this folder, bridge truss problem 2.1. so I am going to copy its path link, and then here file, set work directory, so I'm going to paste it here. Okay, and then I'm going to save this model as bridge truss. So this bridge truss is going to save in your destination folder, so that is being saved. Step in the modeling is to create part, and the 2D deformable wire approximate size is 2 times the maximum length, and then create lines using connected lines. So here to create part you have different options. Here you have 3 options here, so you can click on these tabs to create a part. Then in the module you can go part, and then you can create a part from there, or otherwise here in the model tree you have parts. Double click here, and then you can name it. So truss 2D deformable wire, and approximate size, it must be 2 times the maximum dimension. So maximum dimension is 8 meter, so 2 times is 16, so let's say I'm going to do it 20. Okay, and now it is being drawn in standard XY plane. So now here you have connected lines, and as you move your cursor on that plane, so on that grid, so you can see coordinates. So I am going to start with from here, and then that is the first line 2, and then second line of 2, and then the third line of 2. Okay, and from here, so you can drag. Okay, and then that is the fourth line, sorry, that is fourth line. Okay, so when all these lines are drawn, so then you can fit to zoom to check these lines, and then cancel procedure. So now 4 horizontal lines are drawn here. So the first line, second, third, and fourth horizontal line, and then these diagonal lines. So this is at origin and its coordinate are 1, 2. So I am going to draw that line. So this is 0, 0, and then 1 and 2. So that is one diagonal line, and in the same way I can draw these diagonal lines. Sorry. This one is drawn incorrectly, so I'll click here on erase and then select it and press delete, and then done. So that is being deleted. So again I'm going to draw there, so you can simply, and that's the cancel procedure. So here you have delete, and otherwise you have undo options there as well. So you can use undo option or you can do delete, and then the top horizontal members. So here you are. So all that model is being drawn, cancel procedure and fit to view. And now the next one is you can check the dimensions. Okay, and it's very simple. You can check the dimension. So that is 0, 0, and that is 2, 0, that is 2, 1 by just clicking on the isolated point and moving on these points. Or otherwise you have option here to auto mesh it, auto dimension, and add dimension. So if I want to add dimension, so just select all and it's done, and you can see that dimensions here for horizontal members are 2, and then diagonal members are 2.24. So done, and now you can see that model is being sketched in XY plane. Next step is to create material, and material is a mechanical, elastic, and type is isotropic, and need to add modulus of elasticity and Poisson's ratio. And for material again you have 3 options. You can either go to property module, and in property module you can create material from here, or in the model tree you have material here, so you can create material. So material is, I'm just naming it as, leaving it as it is material. And then here you have mechanical, and then elasticity, and then elastic. And now Young's modulus you need to add, which is 30 gigapascal. So that is 30 e raised power 9, and the Poisson's ratio is 0.3. So okay, and now you can see in the material a new material is being created, and it has modulus of elasticity and Poisson's ratio, and material behavior is elastic, and its name is material. So now material created. Next step is to create section, and category is beam, type is truss, and need to add cross sectional area. So as we have 2 cross sectional area for horizontal and diagonal members, so we need to create 2 sections. I'm going to name them as horizontal and diagonal. So you can create section by 3 ways. Again, in the property module, so you have here create section, then you can create section from there, or otherwise in the model tree, so you can create section from here. So double click on section, name it as horizontal, so beam, and type is truss, continue, and then add cross sectional area of horizontal member, which is 0.045. So that is for horizontal members. So click OK, and now one section is being created. And now I can create a section from here, section, create, Another one, it is section 2 and I'm going to rename it diagonal, and it is beam, category, truss, continue, and need to add its cross-sectional area, so which is 0.02. Okay, so now you can see that horizontal and diagonal sections are being created. So 2 sections are being created. Next step is to assign section and need to select region, select from sketch, and then name as horizontal or as diagonal. So here I am. So here you can assign section from module here, or again here you can go to the part truss and then you can do section assignment. So click on section assignment and it says that here select the region to be assigned section. So I'm not going to create any set. So then I'm going to select all horizontal members. So all diagonal members. So all diagonals member being selected. So done, and then section is diagonal. Okay, so now you can see that. So they are being converted to green. So the next one, I need to select horizontal member, and you can select horizontal member with click and by pressing shift button. So by pressing shift button and click, so you can select horizontal members. So from the selected one, if you have to unselect any, so then keep pressing control button and then click. So now all horizontal members are being selected. So done, and now section is horizontal for them. Okay, so now you can see that it's turned to green. So I'm done with it, and then section assigned. So truss section is to the diagonal members and to the horizontal member. So 2 different sections are being assigned. Next step is to create mesh, and for that need to go seed edge and mesh part and assign element type T2D2. So now again here you have different options. So you can go to mesh module. Here is a mesh module, and then you can create mesh, or otherwise here you can go to the mesh, and here is a seed part or edges. So you can use tab, or otherwise here you have seed part. This is seed part and that is seed edge, or otherwise you can go here in the model tree and click on mesh. So I am going to opt for seed mesh. So seed mesh, click on seed mesh, and it says that select the region to be assigned local seeds. So I'm going to select all of this region. Done, and now it says that how you can method by number, and I am going for 1. So apply, and you can see that a small squares, so they are being added. Apply, and then it's done. The next one is to mesh part, and it says here OK to mesh part. So yes, and now it's being mesh. And then here you have assign element type. So it says select the region to assign element. So I'm going to select all that region. So done, and now you have element library standard and geometric order linear, and I'm going to select from here truss, and then you can see that T2D2 is being selected. So now it's done. So mesh is done. The next step is to, in assembly module, create instance and create instance from parts, and then you need to select parts. So here in the module you can go assembly module. Okay, and then you have here instance. So create instance here, or again you have here in the model tree you have assembly here. So then you can create instance there, or you have option here. So it's a create instance from parts, and then it's already selected. So you need to just click OK, and then you can see that a truss is being added in the assembly. So I am going to just close all these. Okay, so that part is now being assembled. Next step is to create step, and procedure type is journal and static journal. So this is like which type of load you want to apply, and for that you can go here in the module. So step module. So in the step module you can create step here, or otherwise here in the step module, so you can create a step there, or here create a step. So I am going to use that create step here. So I named that as static load, and then initial, and procedure type is general, and then static journal, and continue, and leave that everything default. Okay, so you can see here in this step a static load is being added. Next step is to create field output or modify field output, because only displacement and stresses are required. Stresses are required to calculate member forces, and for that one, so here you have field output request. Here you have field output request. You can have those in the step module. Here is the second one is a create field output, or you can field output manager and you can edit it. Okay, or otherwise it's simple. You can just double click on field output and you will have that sort of stuff. So stresses are required, strains are not required, forces or reactions are not required, so these are not required. And in the displacement, only translational and rotational displacement are required, and in the stresses, stress component or invariants, they are required. So I am going to just select those which are required. So okay, so now field output is being modified. Next step is to create load. So step, you have already created there a static load and category mechanical type concentrate force and select point where you want to apply force. And for that one you have here the load module. So when you go to the load module, so you have create load here, or even here in the model tree you have this load. So I am going to double click on it. So when I'm going to double click on it, so then is a load 1, step is a static load, category mechanical, concentrate force, continue, and now it says select the point for the load. So I am going to select this point where 15 kilonewton load is being applied. So and then done. And now here you have CF1 and CF2. So this is in horizontal direction or in vertical direction. So this 15 kilonewton load is in positive horizontal direction. So I am going to add its value 15 e power 3 and click OK. Load is being applied. So now the next one is a node 3, which is 5 kilonewton, and all these 3 loads are rest. They are in the negative vertical direction. So I go here, create another load. So load 2, static load, category mechanical, concentrate force, continue. I'm going to select this point, done, and here it is minus 5 e power 3. So minus 5 e power 3. So then another load is being applied. So click next load, continue at this point. So done, and it is 7 kilonewton. So minus 7 e3. So 7 kilonewton there, and then the fourth load. Here I can click on the load to create another load. So load 4 is being applied at that point. So it is then minus 10 kilonewton. So now 4 loads, you can see here the 4 loads are being applied. Okay, so you can check or modify their values. So that is 1500. The load 2 is 5 kilonewton, load 3 is 7 kilonewton, and load 4 is 10 kilonewton. So now all loads are being applied. Next step is to create boundary condition, and first step is initial, category mechanical, type, displacement, rotation, and you need to select region. There are 2 sports. Here is a pin sport, the other one is roller sport. So I am going to add both of these sports. So for boundary condition, in the load module you have that second set of boundary condition, so you can create that boundary condition there. So and then boundary condition 1 as pin, and step is initial, mechanical and displacement rotation, continue, and now it says select the region. For the boundary conditions I am going to select that point. So it's done, and now here I am going to set u1 and u2 are equal to 0, because at pin sport both of these both reactions exist, so then there will be no displacement. Okay, so now you can see that here a pin sport is being created. Now I can double click on BC to create the other one, named that as pin, and then mechanical, displacement, rotation, continue, and the other one is roller, continue, and select the region for boundary condition. So I am going to select that point and done. And now for this case, because it's a roller sport, so u1 is free, or in horizontal direction is free, so I am going to just set u2 as 0, click OK. So now you can see that 2 sports are being added there. So now modeling is done. Next step is to create job. So you can rename model or give it name, then data check and submit. So here the model, I can rename that model as bridge truss. So I'm just going to copy it. Okay. And now here you have job in the model tree, or here in the module you can click on job and then you can create a job, or you can double click here on job to create a job, and the job name I'm going to keep as same as the model name. So truss, continue and OK. And here you have now truss bridge. I am going to perform a data check. Okay, so data check is to make sure that you have completed all the steps in the modeling. So it is check running, and for larger models it is always recommended to perform a data check, because once you submit a job and then if there is any error in the modeling, so you can get your result. So here data check completed. Now I'm going to submit the job, and now it is being submitted. After some time status comes as running, and then it will take some time to complete, and then you can see here, so it is completed. Job is now completed. Its mean analysis is done. So now job is completed. Next step is visualization. Field output dialog, and you can visualize displacement stresses. And for that one I need to here click on the job to get your results. So now you are in results, and here are output database, or otherwise in the this is the output database, or otherwise you can go here, file, open, and then you can open ODB, and that is your data file. And here you have field output dialog, and in field output dialog you can select U, and then it shows you that is deformed model, and from here you can change its U1 or U2 horizontal and vertical direction, and S for stresses, and then this is S11, it is normal stresses. So you can visualize your results, and then if you want you can show cross section. So view, ODB display option, and then in the general you have render beam profile. I apply, and then you can see that in 3D, so that is the beam profile. Okay, that is your choice. Apply. So I'm going to uncheck it. Okay, and then you can from here, so you can go to the show element label, show node labels, apply. So you can change their color, like as black to element labels, and then and red to node labels. Okay, apply. So you can see that now there you have. Okay, so apply. You can visualize whatever results you want. Next step in the visualization, you need to visualize displacement values. So you select U in the feed output dialog, and then go to prop values and prop nodes, because reflections are on the nodes, and then components all display, and you can write a file on it. So it's very simple. You can go to tools and query. In the query you have prop values. Okay, you can do like this way, or otherwise here you have prop. So from here in the field output dialog I am going to select magnitude, and then here is a prop value. So when you're going to prop value, so a new window will appear here, and there are different options here. So select from viewport, and I'm going to select a display group, and prop nodes, because deflections are on node, and component all, and then here name group all. So now you can see that here are, okay, so I click here, and then you can see that all the values are being labeled. So for each node, so you'll have different set of values. Okay, so like as just here, if I want to zoom it, so here you have the values. So then these values, if you want to create a write as a file, so I'm going to write a file, and then here you can name it as Truss bridge, and this is going to save in your work directory. So Truss bridge, and then here you can change the number of significant figures and number format, so you can write total, column total, and column minimum and maximum, and okay. So now once you do it, see that Truss bridge report is being created, so you can open it in with the notepad, and you can see here, so like U1 and U2, so here you have all that U1 and U2 values, so X, so like here you have all those values. Now the next step is you need to create a report from field output for variable S11 and then export to the file Excel, and then calculate member forces. So it's simple. I'll go here, stresses S11, and then I can prove values from here. Okay, now I need to select elements and all direct, and then centroid, and display group is all. So now these are like for each element, so these are the stresses which are required, so you can display those stresses from here. Okay, and then you can write to a same file, append to the file, click OK. Now the stresses are imported or written on that report, so that is it. I'm going to click on it, and here you are. Here you have those like stresses, so just need to multiply with cross-sectional area to get member forces. So I'm going to open an Excel file, a new Excel file, and then just copying that part from here, Control C, and copy in Excel, and now in the data text to column fixed with any alignment. So now it's done, and now these are the stresses. And for horizontal members you need to multiply with horizontal cross sectional area, and for vertical diagonal you need to multiply with the diagonal. So let's say I am going to multiply with for horizontal members only. So these are the results I got there, and then here I can change to the general. Okay, so now I have these values. So now see here I have the second one. The second one is member between that. Here is the second member, but in Abaqus what I have, it is 11 member. So what is member force in second member? So you can go here, and it is 18.44, and in ANSYS here it is a number 11. So this one is basically number 2, and it is 18.434. And similarly I can go and check like as this is 4. Okay, and in Abaqus that element is 6, and for 4 it is minus 21.87, and here in Abaqus it is 6, so minus 21.875. so these results are very close, or like they are the same as the solution. So in this way you can verify your results, and that is how to calculate member forces. Now all analysis is done, so you got your results, and then you compare your results with the results in the book, and everything is okay. Now summary of this video tutorial. So I analyzed 2D bridge truss in Abaqus CAE, and I followed these main 3: modeling, analysis, and results. So before doing anything, you need to check that which set of unit you are going to use, and I use Newton meter Pascal. Then you need to set work directory and save model. Then I create part, then I created material, then created section, then assigned section, and then create mesh, and then create instance, then create step, then modify field output to check what is required, and then I created load, then created boundary condition, then created job, rename the model, I performed data check, and then I submit the job, and then using feed output dialog I visualize displacement and stresses, and now using prop value I check the values of displacement, and then for axial forces a report was created, and then that report was exported to Excel, and then stresses are being multiplied with the area of cross section to get member forces. So that's all from this tutorial. Thank you very much for watching. I hope you find this video informative and helpful. So you can leave your feedback in comment section.